Okay, so here's another problem. Now in this problem, you've been given two charges, q and 5q. Okay, let's say that they're separated by some distance d. Okay, and the question is, at what position will you put a third charge such that it is in equilibrium? Okay, so we need to figure out where a third charge needs to be placed such that it's in equilibrium. Okay, also we can ask a question, I mean, does it depend on the sign of the charge? Okay, and the answer to that question is no, it doesn't really depend on what the sign of the third charge is. Okay, whether it's positive or negative. So let's see whether how to figure out where to place it. So first of all, there are a bunch of different regions. Okay, what we know clearly is that we want the two forces due to q and 5q on this test charge to be equal to 0. We know that, we understand that. So we ask the question, okay, where should it go? Now let us look at the different regions here. Okay, so if I have q and I have 5q, okay, let's say if I'm to the left of q. If I'm to the left of q, clearly q repels the charge, and let's our test charge be a positive value. Okay, so q repels it, and also 5q repels it. So clearly anywhere to the left, the two forces are not going to oppose each other. Okay, they could be equal, but they're never going to oppose each other, and as a result, it cannot be to the left. So we know that it cannot be here. Okay, and similarly we can say that it cannot be here, which means it has to be somewhere along the line joining the two. Okay, now it also cannot be anywhere off this line, because if it is off this line, if I'm somewhere here, then the two forces are going they could be of equal magnitude, but they're never going to have the opposite direction. So it has to be along the line joining the two. So we conclude that it's going to be somewhere in between. Okay, so let us just call this distance x. Let us say it is a distance x from charge q, and so it'll be a distance d minus x from charge 5q. Great. Now that we have this, okay, let us basically equate the two forces. Okay, and for test charge is simply some value q0. So for it to be in equilibrium, we know that the forces are going to have the same magnitude. Clearly the directions are going to be opposite in between the two. Okay, so the forces are going to be k times q times q0 over x square, and this will have to be equal to k times q0 times 5q over d minus x the whole square. Great. A lot of things cancel out. Okay, you see, first of all, the q0s cancel out, which we want. It should not depend on q0. The k cancels out. Okay, if one of the q's cancels out, so you end up getting an algebraic equation that looks like this: 1 over x squared is equal to 5 over d minus x the whole square. There are several ways of solving this. Okay, so I'm just going to do the one. First of all, let's cross multiply everything, and what you end up getting is you get d minus x the whole square. And what I'll do is I'm just going to leave my x here, so it'll be d minus x over x the whole square is equal to 5. Make sure you understand this. Okay, so what I have is I'm just going to write this again as two terms. I'm going to write this as d minus x square and then x square. Okay, so this ends up giving us d minus x over x the whole square is equal to 5. Now here, instead of doing this, you could have also set up a quadratic equation and done the problem, but I'm just going to use a slightly different rule, just because, again. Okay, so once we get this, what we have is we have d minus x over x is equal to plus or minus square root of 5. Okay, we have two choices. So we have d minus x equals square root 5 times x, or d minus x is equal to minus square root 5 times x. So now I have an algebraic, so d is equal to x plus square root 5 times x, or d is equal to x minus square root 5 times x. So this one implies x is equal to d divided by 1 plus square root of 5, or this implies x is equal to d divided by 1 minus square root of 5. Okay, clearly the second value is negative, and if x is negative, it means it is to the left of the charge. Okay, what it's actually telling us is that there is a location there to the left where the electric field has the same magnitude, okay, due to the two charges. However, this region we already argued is not allowed, because in this region the two forces are not going to be opposing each other. Okay, so what this does is, since we equated only the magnitudes of the forces, obviously we expect the magnitude to be equal in two areas, and it happens to be that it's going to be equal in this area. Okay, on the other hand, this d over 1 plus square root 5, this is a number less than d, which is exactly what we expected. So correct answer to the problem is this. Okay, now once again, you could have done the whole thing using a quadratic equation, which is totally fine. Go ahead, do it, check your answer, and make sure you get the same thing. Okay, great. I hope this helps.